Okay, right on time. Let me start with sort of a public service announcement, and then we'll get into today's colloquium. A few weeks ago, unfortunately, the snowstorm that closed the observatory also had the effect of forcing us to cancel what I thought would be a particularly interesting colloquium for our observatory by Dava Sobel, the author. And she has recently written a book about the women of Harvard College Observatory, and she has kindly agreed to reschedule that talk for Wednesday, March 15th from 2 to 3 o'clock. So that will be a special colloquium. And we'll, of course, send around a notice, but I thought I would alert you to that.
Cookies?
So, cookies? We're in negotiation.
She has an agent.
Is that truly the deciding factor? Well, it's both a professional and personal pleasure to welcome today's colloquium speaker, David Neufeld. David graduated from Cambridge University in 1983, whereupon he joined us here at the CFA for his PhD work under Alex Delgarno. David finished his PhD work in 1987 and proceeded to a postdoc at UC Berkeley for 2 years before leaving Berkeley for Johns Hopkins University, where he is currently a faculty member. David's association with the CFA, though, did not end in the 70s. David was a Bach Prize winner in 1996, and he served on the visiting committee for the Smithsonian side of the house in 2011. But as I'll mention in a moment, his visits to the CFA have been far more numerous than that. His primary research interests are in the area of molecular astrophysics, astrochemistry, and interstellar medium. And David has been particularly productive and made major contributions in the area of radiative transfer, interstellar shock waves, interstellar and circumstellar chemistry, astrophysical masers, and observational studies at submillimeter and infrared wavelengths, including use of the submillimeter wave astronomy satellite, which brought him to the CFA on a regular basis in the 1990s and 2000s to work with our group. He was also heavily involved in the Infrared Space Observatory, Spitzer, Herschel, and most recently Sophia. Today, David is going to tell us about how interstellar chemistry, when carefully studied, and I would add cleverly studied, which he has done, can tell us about interstellar environments such as the relative fraction of molecular and atomic gas in the interstellar medium, the cosmic ray density in the galaxy, the intensity of the UV field in various places in the galaxy, and turbulence in the interstellar medium. Before having David assume the podium, I'll just mention and reiterate what's up here. David, unfortunately, will be leaving to attend a meeting after this colloquium and won't be around tomorrow as usual, but he will be returning to the CFA on a weekly basis starting in mid-March through mid-April. And as he notes here, he invites you to get a hold of him at his office at 208 at 160 Concord Ave. With that, David.
Right. Well, thanks very much, Gary. It's a pleasure to be back here. And I have many memories of sitting in this room on Thursday at 4 o'clock as a graduate student and learning a lot of very interesting astronomy and astrophysics. So what I wanted to talk to you about today are small interstellar molecules and what we can learn from them if we listen carefully to what they have to tell us. So what I'll start with is an introduction to the rich chemistry of the interstellar medium, and then I'll turn to ways in which we can probe, and I'll refer here specifically to the diffuse interstellar medium, with small hydride molecules, by which I mean molecules containing just one heavy element atom and one or more hydrogen atoms. And there's a number of applications I'll discuss, and then I'll summarize and talk about some of the future directions that will become possible. So let me start with astrochemistry. And there have been more than 190 interstellar molecules discovered over the last 80 years. And here's a list that is maintained by the Cologne database for molecular spectroscopy, showing all of the molecules that have now been detected from the interstellar gas, starting with the smallest and ending up with the largest molecules. I constantly have to renew this with smaller and smaller font size to be able to fit it all on one page, but you can still do that. And there's a variety of different types of molecules that are seen, some very familiar that you could find in the grocery store or the liquor store. So the sodium chloride, water, acetic acid, ethanol. And some of these molecules are very exotic. In fact, some of them, for example, cyclic C3H, were discovered first, if you like, as unidentified lines in the radio spectrum and only subsequently characterized in the laboratory. In fact, it was this laboratory here. So there's a broad range of molecules, and the larger ones tend to be organic. So this may, when you first look at this, sort of just have an element of stamp collecting, you know, what interesting things have we found? But what I hope to convince you today is that carefully interpreted observations of interstellar molecules can give us unique information that's of general astrophysical interest. And I'll also argue that the smallest molecules, the simplest molecules, basically show the greatest promise for advancing our understanding. So there's sort of a game plan, if you like, in molecular astrophysics, where we're going to observe astrophysical molecules, measure their emission line luminosities, or perhaps their absorption line optical depths, and then compare what we see with detailed physical and chemical models of the various environments where molecules are found. And those include diffuse interstellar clouds, dense clouds, photodissociation regions, circumstellar outflows, X-irradiated regions. And one has to do a lot of modeling of how the molecules are excited and how the radiation they emit is transferred. And another key ingredient that makes this quite a multidisciplinary field is that one needs a lot of basic physical and chemical data. One needs spectroscopy to be able to identify molecular lines, collisional rate coefficients, reaction rate coefficients. One needs to understand grain surface reactions, and photoionization and photodissociation, which destroy molecules. So, but the idea is that combining these three elements, we can extract information of general astrophysical interest. Let me just say a few words about my collaborators on much of the work that I'm going to be describing today. There are a couple of key programs of the Herschel Space Observatory. One was called Prismus and one was called Hexos. These are all acronyms, the meaning of which I can't remember. The PIs were Mary von Geran and Ted Bergen. And then there's a lot of fantastic data coming now out of Sophia, where I've been working with the GREAT team led by Rolf Gusten, and the EXIS team. These are two different instruments led by Matt Richter. There's also some ground-based observations that were carried out by Nick Indriolo, who was a postdoc at Johns Hopkins and now a research scientist across the street at Space Telescope. And then a lot of theoretical effort, and particularly I'd like to highlight the work of Mark Wolfire at the University of Maryland, who's been a collaborator on much of the theoretical work that I'll talk about. So this field that I'm going to discuss has really been opened up by new observatories that have allowed us to perform spectroscopy at submillimeter wavelengths over the last 7 years. And three that I'll particularly emphasize are the Herschel Space Observatory, which had a heterodyne spectrometer called HiFi, the SOFIA, NASA's Airborne Observatory, and in particular the great heterodyne instrument that is operated by Max Planck Institute for Radio Astronomy and University of Cologne, and then the APEX submillimeter telescope at a superb site in the Atacama Desert, again operated by the Max Planck Institute. And this, of course, now is being superseded by, or complemented by, ALMA nearby. But these three facilities have led to the discovery of 8 new molecules in the diffuse interstellar medium that I've listed here. And you'll notice that all of them are hydrides, as I defined it before. And the reason is that hydrides have small momenta of inertia, and therefore they have high frequencies of their low-lying rotational transitions. And these high frequencies are inaccessible from most sites on Earth, or all sites on Earth, depending on the transition. And that's mainly because our atmosphere is full of course, one very important hydride, water vapor. So a lot of the observations that I'll describe were obtained by means of absorption line studies of a bright submillimeter continuum source that we're not necessarily interested in. So we can use a very luminous region of massive star formation with a lot of warm dust as, if you like, a background laboratory lamp. And then we can search for absorption along the sight line to that background source by foreground material that typically lies in spiral arms that are intersected by our line of sight. And because of the differential rotation of the galaxy, there are Doppler shifts that allow us to distinguish different components along the line of sight. And this is a very clean experiment that provides very robust measurements of the molecular column densities, because at the density of this gas, most of these hydride molecules will be in the ground state. And that makes things rather simple. So here's an example of the types of observations that can be obtained. The top one is from the GREAT instrument on the SOFIA Airborne Observatory, and the next 3 are from the 30-meter IRAM telescope at lower frequencies. And these are spectra obtained of 4 sulfur-containing molecules. This was the discovery of the SH radical in absorption. And then for many of these molecules, one sees emission from the background source, very strong emission. And then these tiny little absorption features, which I've expanded here, are still observed at very good signal-to-noise ratio. So one can measure very precisely the amounts of all 4 of these molecules in a number of different diffuse clouds along the sight line. And observations such as these then allow us to determine the relative concentrations of these various molecules relative to hydrogen atoms or hydrogen molecules. And that's what's shown in this table here, which is from a recent annual reviews article we had on interstellar hydrides. Marie von Geran is the first author. One thing you'll notice, this first column is the abundance relative to hydrogen or H2. And this second column shows you what fraction of the heavy element in question, carbon, oxygen, nitrogen, etc., is in the molecule in question. And typically it's a very small fraction of, say, oxygen would be in water, less than, almost in all cases, 1 part in 1,000, except for 2 notable exceptions, fluorine and chlorine, that I'll discuss shortly. So most of the heavy element atoms are in atomic or atomic ion form, and just a small fraction in these molecules. But as I mentioned, even though they're not a major reservoir of the interstellar gas in these diffuse clouds, they can provide unique information, and each molecule has a slightly different characteristic that is really all controlled by thermochemistry, that is the relative bond energies for various different molecules, because a small difference in those energies, in other words, in thermochemistry, can lead to a large difference in the chemical behavior that these molecules exhibit in the interstellar medium. So I'll now turn to sort of the meat of the subject and start with the first of the four topics I wanted to discuss, and that is molecules that can be used to trace molecular hydrogen, which is the dominant constituent of the interstellar medium, but which is very difficult to observe. You can observe it in the ultraviolet towards nearby stars, but you can't go very far in the disk before the extinction is too large. And then at infrared wavelengths, its transitions are just quadrupole allowed, so they're very, very weak. So it'd be nice to have another way of measuring the amount of hydrogen that we see. And there's one molecule that sounds kind of unlikely on the face of it that is very useful for this purpose, and that is hydrogen fluoride. And fluorine, as you may know, is not a very abundant element, but this particular molecule is very abundant because of some aspects of thermochemistry that are shown in this table. And I'll return to this table a few other times and sort of explain it a little bit each time. But the first cell in this table I wanted to draw your attention to is this one here, and it's colored green because it tells us that the reaction of fluorine with molecular hydrogen is exothermic, meaning that you get energy out of the reaction. So it can proceed at low temperature. And the other thing that's shown here is the ionization potential, which in the case of fluorine is larger than that of hydrogen, 13.6 eV. And so that means that fluorine atoms will be shielded from ultraviolet radiation capable of ionizing them. And therefore, all the atomic fluorine in the interstellar gas will be uncharged, and it can react with H2 to form HF. That's a very well-studied reaction, both in the laboratory and theoretically, and it's quite rapid at low temperature, even though there's a barrier. The sort of quantum mechanical tunneling effects mean that fluorine will quite rapidly react with H2, which is the dominant constituent of these clouds, to form hydrogen fluoride, which we can detect with Herschel. And hydrogen fluoride is destroyed only slowly. It can react with carbon plus to form this molecular ion, which is called fluoromethylidinium. Really rolls off the tongue nicely. It sounds very exotic. It's actually isoelectronic with carbon monoxide, which is sort of the most widely observed molecule there is, and it can be observed and has been observed at radio wavelengths. So what this reaction network means, and particularly the exothermicity of this reaction, which is why I've colored it in green, is that hydrogen fluoride will be a major reservoir of fluorine wherever molecular hydrogen is abundant. And so it makes a beautiful tracer of molecular hydrogen. And that sort of explains this very anomalous entry in this table where you see hydrogen fluoride accounts for typically 40% of all the fluorine in diffuse clouds, whereas that's quite different from any of the other molecules. And so one could observe this with Herschel. There's a transition at 1232 gigahertz that is the J equal 1 to 0 transition. And here's observations of a source, W51, which is a background source. And then you see all this absorption by material along the sight line to that source. And this is a very high signal-to-noise ratio. All these little wiggles are real. And the top spectrum shows hydrogen fluoride. The bottom spectrum shows water vapor. And remarkably, you can see the hydrogen fluoride absorption is actually stronger than the water absorption, even though the abundance of fluorine as an element is 4 orders of magnitude less than that of water. And this basically just reflects this key thermochemical fact that hydrogen fluoride is more strongly bound than H2. So you can have an exothermic reaction to produce it. If one constructs a model of this, as Mark Wolfire and I did, here's a model of a diffuse or translucent molecular cloud showing the abundances of various species on a logarithmic scale as a function of depth into the cloud. And you can see you don't have to go very far into the cloud until molecular hydrogen becomes a main form of elemental hydrogen. And you have to go much further until you get a significant amount of carbon monoxide. And if you look at our predictions for hydrogen fluoride, you can see that that's coming up very close to the cloud surface, more or less exactly tracking molecular hydrogen. And then one gets this CF plus in the region of overlap between the hydrogen fluoride and the carbon plus that is present close to the cloud surface. So this is quite a dramatic effect at this point here. There's more hydrogen fluoride than carbon monoxide, despite the elemental abundance differences. It's been possible to calibrate the amount of hydrogen fluoride relative to the amount of molecular hydrogen by observing, there's a single sight line in which we can observe them both in absorption, and it's this diffuse cloud in front of the star, HD 154368, which was observed by Nick Indriolo and collaborators. And here he observed, actually from the ground, a vibrational band of hydrogen fluoride at 2.5 microns that you can see in absorption here and here. The frequency changes with Doppler shift of the source relative to the Earth. And one also had ultraviolet measurements of H2, so one could determine the abundance of hydrogen fluoride relative to H2. And it was about 40% of the abundance of elemental fluorine, in excellent agreement with the models. So that's sort of the first application, hydrogen fluoride as a probe of molecular hydrogen in the interstellar gas. There are other molecules that can probe other aspects of the interstellar medium. And the next one I wanted to turn to are three molecules that can trace gas that is at temperatures much higher than the typical temperature of the diffuse interstellar medium. And these are molecules of the elements carbon and sulfur. So if we go back to this thermochemistry table, as I will in a minute, what we see is that neither carbon ions or singly ionized sulfur nor sulfur atoms can react exothermically with H2. They have endothermicities, energy barriers that must be overcome before the reaction can take place. And so they would be negligibly slow at, say, the typical temperature of a diffuse interstellar cloud, which is about 100 degrees, right? Because you would have a factor e to the minus this huge number over 100 degrees would give you the number of colliding atoms that have enough energy to overcome the barrier in a Maxwell-Boltzmann distribution. So that's sort of indicated in these red boxes, which basically indicate an endothermic reaction for carbon plus H2, for sulfur plus H2, and also for sulfur plus H2. So it's very hard to have any reactions of these at low temperatures, and yet we observe the products of those reactions. We observe these molecular ions CH plus and SH plus, and also, as we discovered with Sophia, SH, and the abundances are orders of magnitude greater than what would be expected at the average temperature of the diffuse interstellar medium. And what this has been considered evidence for is either that some small fraction of the gas has an elevated temperature, or in the case of carbon, of CH plus and SH plus, that there's a drift between the ions, carbon plus and sulfur plus, and the neutral species in the interstellar gas. And this sort of goes into models of interstellar shocks, as I'll explain in a minute. So here are some, I mean, it was long been recognized that the abundance of CH plus is anomalous. And so recently SH plus and SH have been added to the picture and corroborate the presence of a ubiquitous warm chemistry. And some of the early models for CH plus are shown here. This shows you the abundances of various molecules behind a shock front. This is from Drain and Katz. And this curve here is CH plus, which you'll see is greatly increased in the warm part of the shock that is sort of in this region here. And similar results apply also for SH plus and SH. So basically what the recent observations have shown is that they corroborate the existence of this, quote, warm chemistry and indicate that the gas has to be warm enough, in fact, to make these molecules as well as CH plus, which requires an even higher temperature. So that could be an important constraint on the dissipation of turbulence in the interstellar medium. The next example I want to give of information that one can obtain concerns the cosmic ray ionization rate, and I'll spend the most time on this subject because it's something I've just submitted a paper with Mark Wolfire on. So it's been known for a little over 100 years that cosmic rays are an important ingredient of the galaxy. They were discovered by Victor Hess in 1911 and 1912. He made a series of balloon flights, one of which is shown here. So a couple of notable things that I'm sure will be of interest to people who've worked like Giovanni and Gary and Josh Grinley, if he's here, on balloon flights, which I know is an important part of the heritage here at CFA. The first thing is to notice the gondola in this case is a wicker basket, and the PI is inside the gondola. And so Hess went up actually to an altitude as high as 17,000 feet with an electroscope to measure the ionization rate. And the expectation was that it would decrease as you went up because it was believed that the dominant source of ionization of the air was from radioactive materials in the Earth. But actually, the ionization rate increased. And it was some time until the true nature of the cosmic rays was recognized. There was a debate between Millikan, who wrongly thought it was gamma rays, and his student Compton, who claimed a latitudinal dependence that would indicate that they were charged particles. And in fact, it was Compton was right. And now we know that these are charged electrons, protons, and other ions that actually span a huge range of energies from energies of MeV up to the most energetic cosmic ray ever detected to date, which had an energy of 50 joules. So that's the energy of a fastball pitched in Little League Baseball in one proton. So there's a Lorentz factor here of 10 to the 10, I guess, or 10 to the 11. Cosmic rays actually have a larger energy density than starlight. So here's a little figure or table from Drain's book on the interstellar medium. And it's amazing, actually, all these things have roughly an energy density of 1 electron volt per cubic centimeter. There's the cosmic microwave background, there's starlight, there's the thermal kinetic energy of the interstellar gas, there's magnetic energy, and cosmic rays are actually at the top of that. And they interact with the interstellar gas in various interesting ways. So above a threshold of about 280 gigavolts, cosmic rays create gamma rays first by producing neutral pions that then decay to emit gamma rays that can be detected, for example, by the Fermi satellite. And of interest to the present talk is the lower energy cosmic rays can ionize and also heat the interstellar medium. So they'll interact with a hydrogen atom to give a proton, or a hydrogen molecule to give the H2 plus molecular ion. And there are also secondary electrons that can further ionize and heat the gas. So it's a very interesting question, and the key parameter is what is the rate at which cosmic rays ionize the interstellar gas? So that's the cosmic ray ionization rate that I'll abbreviate CRIR. And there's various different ways that this can be characterized. You can talk about the primary ionization rate per hydrogen atom, or the total ionization rate, including secondary electrons, or the rate per molecule. And unfortunately, people are not always scrupulous in saying which of these they're quoting. We can also ask then what cosmic ray ionization rate is expected. And you would think this would be quite easy now that we can measure cosmic rays, say from a balloon experiment or from a satellite in orbit around the Earth. But the problem is that the ionization rate is dominated by lower energy cosmic rays than any that can be detected. And particularly at the location of the Earth, the cosmic ray flux is modulated by the sun's magnetic field and the solar wind, which reduces the flux of cosmic rays below 1 GeV. So you can sort of get around that final effect a little bit by making in situ measurements. And now the Voyager 1 spacecraft is more than 120 astronomical units from the sun, and there's been a substantial increase in the flux of cosmic rays that it has measured at low energies. So this figure here shows the spectrum for observations at 1 astronomical unit, in other words, close to the Earth. And then this is what is now seen from the location of Voyager. But it's unclear. I mean, I put 122 because that's sort of the distance at which a sudden increase was seen and may be interpreted as crossing the heliopause. But it's unclear exactly whether one is still seeing a completely unmodulated cosmic ray flux, even from Voyager 1. And also, the cosmic rays that actually ionize hydrogen, and the cross-section is shown here, are at lower energies than the energies that can be observed from Voyager 1. So an extrapolation is needed. If you make that extrapolation, you get a rate of about 10 to the minus 17 ionizations per hydrogen atom per second. But as I say, there are these caveats about the ionization cross-section, not clear whether one is still or one is yet seeing the unmodulated rate. And in any case, any measurement that you make from the solar neighborhood obviously need not apply to interstellar gas clouds far away. So people have tried to estimate the cosmic ray ionization rate using chemistry, using astrochemistry. So the idea is you look at molecules, and particularly molecular ions, in molecular clouds, and you choose ions that you think are formed primarily as a result of cosmic ray ionization. So this was done quite a lot in the dense interstellar medium. And here's an example from van der Dak and von Dissuk, where they got a result that's pretty much in exact agreement with the extrapolation from Voyager. This is per H2, and the other one was per H. So these are, in fact, in amazing agreement. So this would look like a great victory, but what was then realized about 15 years ago is that if you look at a molecular ion that comes from a less dense molecular cloud, the H3 plus molecular ion, which was pioneering work done by Oka and McCall and Nick Indriolo. From observing that molecular ion, you infer a much higher cosmic ray ionization rate, an order of magnitude higher. But these observations apply to a less dense type of interstellar cloud. So there was a very influential review by Snow and McCall in 2006 where they established these definitions. So as you go from the most diffuse interstellar clouds to the densest, well, the most diffuse are called diffuse atomic clouds, where the hydrogen fraction is less than 10%. And then there are diffuse molecular clouds, which aren't thick enough to have CO in them, but do have significant amounts of molecular hydrogen. And then there's an intermediate case they define translucent clouds. And then there are the dense molecular clouds that are the sites of star formation. So the first measurement applied to the dense molecular clouds, and the H3 plus measurement applied to somewhere on the borderline between diffuse and translucent molecular clouds. And there's this discrepancy. Maybe it's some error in our understanding of the chemistry, or maybe it is that the cosmic rays are excluded from dense molecular clouds by shielding or effects involving interaction with alphane waves. So let me talk a bit more about this H3 plus molecular ion. The picture for how it's made is that hydrogen molecules are ionized to give H2 plus, and then H2 plus will transfer a proton to a hydrogen molecule and make this H3 plus molecular ion, which is somewhat more stable but is destroyed by dissociative recombination with electrons, or it can transfer its proton to something with a lower proton affinity like carbon monoxide or atomic oxygen. So we've reanalyzed that with the use of diffuse cloud models that Mark Wolfire has developed. And we basically get results that are quite similar to McCall and Indriolo. And in addition, we find that there's sort of marginally significant evidence for a decline in the cosmic ray ionization rate, which is plotted here on a logarithmic scale, with the amount of shielding H2. As I say, it's marginally significant, a sort of 3 sigma significance to the slope being less than 0. But if you did follow this slope, by the time you get to a dense molecular cloud, which would be somewhere over here, you would indeed have a cosmic ray ionization rate of around 10 to the minus 17, which is what was computed. Well, there's another way of getting at this, and that is from observations of molecular ions that are present in this diffuse atomic component. And there are several of those, and in particular OH plus and the first interstellar molecule known containing a noble gas element, ARH plus, argonium, protonated argon, have been observed. And you'll see these cells referring to the reaction of O plus or argon plus with H2 with being exothermic. That's why this is green. The reason it's shaded is that it involves an ion that is not present ordinarily or in great concentration in the diffuse interstellar medium, because in both the case of oxygen and argon, the ionization potential is above that of hydrogen. So the only way of getting oxygen or argon is actually if cosmic rays are present to ionize a gas, because there's no ultraviolet radiation that could ionize oxygen or argon. So I'll take a sort of 2-minute digression. You may be surprised to hear about argonium if you haven't been following this very closely. So this is the first known interstellar molecule containing a noble gas atom. I mean, 50 years ago, it was believed that the noble gas elements could not form any molecules, but that's certainly known to be untrue now. But this is the first time one has been detected in space. And in fact, it was an amazing story I won't have time to go into, but there was this unidentified spectral line at 617 gigahertz that was very widely observed in diffuse interstellar clouds. And for several years, no one on the teams that I was involved with could figure out what it was, even though we had some of the best spectroscopists, astrophysical spectroscopists, Holger Muller and John Pearson. And through a series of missteps that you can ask me about afterwards, it was not identified until Mike Barlow detected this line and another line at exactly twice the frequency from the Crab Nebula. And that basically made it clear that it was argonium. It's rapidly destroyed by H2 because unusually argon has a lower proton affinity than H2. So this reaction goes in the forward direction. And so it's very odd, but argonium is actually predicted to be a fantastic tracer of almost purely atomic gas. It reaches its maximum abundance when the hydrogen fraction is only about 1 part in 10 to the 4. So if you want to find gas in the interstellar medium that is 99.9% atomic, you shouldn't look at H1 with the 21 centimeter line, because that might not be atomic. It could be 50% molecular. You want to look for a molecule, and that's this molecule. But for present purposes, it's important because it helps us probe the cosmic ray ionization rate. And then the other one is oxygen. So oxygen, actually what happens with oxygen is that a cosmic ray can ionize hydrogen to make H+, and then there's a charge transfer reaction that is slightly endothermic, but only by a couple of hundred degrees, that produces O+, OH+, and then H2O+, and H3O+, by a series of reactions with H2. And so by looking at the measured abundances of this ion and these two ions that we could observe with Spitzer, and then interpreting this data with a very detailed model, we could obtain an estimate of the ionization rate per hydrogen atom in these diffuse atomic clouds that are more than 90% atomic typically. And remarkably, it's in excellent agreement with the value obtained from H3+, supporting the idea that indeed the diffuse interstellar medium has a cosmic ray density, at least of low energy cosmic rays, that's much higher than the dense interstellar medium. There's one other way of trying to get a handle on the cosmic ray ionization rate, and that's actually through observations of atomic ions. And so, as I'm sure you well know, there are radio recombination lines that can be observed. And if you go to very long frequencies, you can actually observe lines of very high principal quantum number, as high actually as 600. And they're detectable from diffuse atomic clouds that are mainly atomic rather than H2 regions. It's kind of amazing to think of these atoms. The size of the cloud of electrons goes as n squared. So these are atoms at about 20 microns in size. They're very subject to pressure broadening. And you can observe them in hydrogen, but you actually see them even stronger in the case of carbon atoms. So these are Rydberg atoms where 5 of the 6 electrons are where they usually are, and then the final electron that has just been captured is in a state of very high principal quantum number. So these are called Rydberg atoms. And if you're that little electron at 20 microns away from the nucleus, you don't see 6 protons and 5 electrons. You just see a charge of +1. It looks exactly like a hydrogen atom to you. And so your energies are exactly the same as for a hydrogen atom, except that you have a smaller reduced mass because the nucleus is 12 times as heavy as hydrogen. And that gives this shift where you see the carbon ions, the carbon recombination lines at different velocities. So this has been done now with the Westerbork synthesis array and also with LOFAR by Unk et al., a group involving Xander Thielens. And you get a lot of information from such observations. You get line widths, which tell you the density and temperature of the gas. You have the relative line strengths as a function of the principal quantum number of the electron concerned. And most important, you get the ratio of the hydrogen to carbon radio recombination lines. And that gives you a probe of the cosmic ray ionization rate, because the carbon recombination lines come from the recombination of carbon plus, and carbon plus is ionized by UV in these clouds. So that has nothing to do with cosmic rays. But the hydrogen recombination lines come from H plus, which is produced by cosmic ray ionization. So here, these radio recombination lines as a function of principal quantum number, and the line widths show you or allow you to determine the temperature and density of the gas. And then from the strength of the carbon recombination lines, you get the emission measure, that is the integral of the density of carbon plus times the density of electrons along the line of sight. And then you can look at the ratio of emission measures for hydrogen to carbon, and that probes the cosmic ray ionization rate. And in this recent paper, Unk et al. Obtained a very, very strict and weak lower limit of just a few by 10 to the minus 18 on the cosmic ray ionization rate, because they assumed that the hydrogen is destroyed only by radiative recombination. But in the detailed models that Mark Wolfire has developed, there are two additional processes that are much more important in removing H+. One is charge transfer with these small grains or large molecules, the polycyclic aromatic hydrocarbons, and another is that charge transfer reaction I mentioned with oxygen. And that greatly increases the cosmic ray ionization rate you need to produce this ratio, way above this strict lower limit, and that's shown in this plot. So these are the models from our, these are the results from our detailed model. This is the observed value, and these are models with different parameters, but they're all in this range around a few by 10 to the minus 16 for the cosmic ray ionization rate. If you didn't include the other destruction mechanisms for H+, this is the curve that you would get, and this was the basis for Unk et al.'s result of just a few by 10 to the minus 18. So based on the detailed model, this is our best estimate of the cosmic ray ionization rate. So everything is really, and you might say this is a little fortuitous because some of the reaction rates are not known that well, although they're being worked on. But basically, there seems to be now a remarkable accord as to the cosmic ray ionization rate in the diffuse interstellar medium, and that has implications for the propagation of cosmic rays. Well, the final topic that I'll just touch on briefly, I've already alluded to a little bit, is the use of these types of measurements for getting the molecular hydrogen in the interstellar gas. So if you look at this diagram again that I showed previously, and in particular think about this molecular ion OH+, two things can happen to it. It could react with H2 to make H2O+, which is another ion that we can measure with Herschel, or it could be destroyed by electrons. Now, the number of electrons in these clouds will roughly equal the number of carbon nuclei, because most of the electrons are provided by carbon plus. And so there's a competition between hydrogen and electrons, and the latter have a known concentration. And if you measure the ratio of H2O+ and OH+, you can measure the fraction of OH+ that will be destroyed by H2 versus that destroyed by electrons. And the observed ratios imply that only about 2 to 10% of the gas is in the form of H2 in the clouds where we measure OH+ and H2O+. So what we're planning to do is we've now worked this out for various different molecular ions, including some containing the element chlorine, which we could observe with Spitzer and Sophia. And they each peak at a different molecular hydrogen fraction, which is what's plotted logarithmically on the x-axis. And this is a linear scale for the abundance. So if we had some distribution of molecular hydrogen fraction in the interstellar medium, we can sort of convolve it with these different filter functions, if you like, and then get an idea of what that distribution function is for the molecular fraction by observing all of these different molecules. So that's currently underway. But what we've already done with OH plus and H2O plus and argonium is shown that there's at least two constituents that we can identify. One is mainly atomic clouds with, as I said, an H2 fraction of just a few percent, and that's traced by the OH plus and H2O plus. But in gas with this much H2, you'll see very little argonium. And so there must be almost purely atomic clouds, more than 99% atomic, that are traced by this argonium. So those are four examples, and let me summarize what I think we've learned now from recent molecular observations, specifically of the diffuse interstellar medium. We can reliably trace H2 at submillimeter wavelengths, where you can look clean across the galaxy without worrying about extinction by observing this molecule HF. We've confirmed that there's a warm chemistry operating in the interstellar medium that is associated with the dissipation of turbulence, for example, in shocks, and additional constraints must be provided by the fact that we see SH and SH plus that are even harder to produce than CH plus. We've confirmed that the cosmic ray ionization rate has a typical value that now seems to be a remarkable concordance between about 2 and 3 times 10 to the minus 16. So that's an order of magnitude larger than what was believed a decade ago, than what you measure in dense clouds, or than what you would expect from a simple extrapolation of the cosmic ray spectrum observed by Voyager 1. And finally, that a substantial component of the diffuse interstellar medium has a very small H2 fraction. So let me just say, or show two slides about future directions. Herschel is now defunct. It was cooled by a giant dewar of liquid helium that ran out in 2013. But one of the things that we can now start to do is look in galaxies at high redshift at those transitions that cannot be observed from Earth's surface, but which are redshifted to observable wavelengths in the high redshift universe. So, for example, there's this fantastic case of a disk galaxy at a redshift of 0.9 that lies in front of a quasar at a redshift of 2.5. And one can observe many, many molecules in this, including molecules that would be blocked from the Earth at redshift 0, but are quite easily detectable, shifted to eminently observable frequencies from ALMA. And so this gives a lot of interesting physics that we hope to exploit, and it allows you to measure, for example, isotopic ratios in the case of H2Cl+, and give you some handle on the history of stellar nuclear synthesis to high redshifts. And then finally, with Sophia, we can perform heterodyne spectroscopy, both at the in principle at the frequencies that were previously accessible with Herschel, but also at frequencies that were not covered by Herschel. And in particular, there was a gap in coverage of Herschel. Herschel's coverage is in yellow for heterodyne spectroscopy. And this is great, and there's one molecule was discovered with great because it lay in this gap between the Herschel receivers, and then one can push to higher frequencies than any that were accessible to Herschel Hi-Fi. And then in the future, they're going to, as I say, be pushing to lower frequencies where one can follow up on some of the studies that were done with Herschel. So let me finish there, and I'll be happy to take questions.
Thank you, David. Questions?
This may show more my ignorance than anything else. Voyager 2 was leaving the solar system at some point, well different from Voyager 1. What does that show?
Right, so I don't think it's, I'm not that familiar. It hasn't reached the heliopause yet. But I think that will be interesting, but I don't know when that's expected to occur. But it isn't there yet, I know that.
Charlie?
Yeah, could you comment on what you said was the ubiquitous WAM chemistry for the diffuse ISM? Are you sure that it's really ubiquitous, or are usually the lines of sight you pick are towards those stars, I would imagine?
Well, some of them are, when CH plus is observed optically, they tend to be relatively nearby stars. But in the submillimeter, where we can also observe CH plus and SH and SH plus, we're looking along long sight lines. I mean, one of them is W49, which is 11 kiloparsecs away. So we're intercepting many spiral arms along the line of sight. So I don't think there are great selection effects associated with the choice of background laboratory lamp, if you like.
So would you then say that the diffuse ISM, the bulk of it has been processed in shocks of 4,000 degree chemistry?
Well, you don't need, I wouldn't say the bulk of it is at 4,000 degrees. In fact, that's clearly not the case. But it seems that almost every cloud that you can find has within it a shock that has elevated the temperature in some small fraction of the volume. So that you can't have a decent sized cloud that doesn't have some gas at higher temperatures, 1,000 degrees or something like that. It's kind of interesting.
Charlie, did you?
In the high Rydberg atoms and the atomic clouds, does the pressure broadening dominate over the droplet broadening?
Yeah, well, as you get to high enough principal quantum number, yes. Yeah.
Also, those Rydberg atoms, those huge sizes change your reaction cross-sections enormously, surely. And does that change your chemistry?
Oh, well, they're just a small fraction of the total, so I don't think that's a significant effect. Right, so we're really looking like a very small fraction of the hydrogen atoms would be in anything other than the ground state.
So we have very complicated molecules of diffuse gas like C60 plus. So
Yes.
in light of this and that discovery, what's your, do you have an opinion on the other diffuse gas? Very strongly, what they might be.
Right, so, well, you know this better than I do, but so I think, in the last year probably, we've had really a confirmation for the first time, or absolutely clear confirmation, that some of the diffuse interstellar bands are due to C60 plus. And that was they were known for many times. The suggestion was made 2 decades ago by Aaron Freund and Foyne, and it's the better laboratory spectroscopy where they could see the C60 plus in the gas phase, not in a matrix, basically made that absolutely clear. So then I guess the question is, are the other lines similar molecules or are they different molecules? There has to be a large class of different molecules responsible for these diffuse bands. So I think it's an open question. And if you ask me where does this C60 plus come from, I really don't know. So,
But I mean, you don't think it's a top-down or bottom-up?
I would guess that it's top-down, that you start with carbon, some kind of carbonaceous material that's made in carbon-rich stars, and that Yeah, because I don't see how you would, at these low densities, start with small molecules and build up to C60 plus.
On one of your last slide, you showed this redshift 0.89 galaxy
Yeah.
in front of Quasar. Are there any perspectives at present to do sort of blind studies of intergalactic material
find
using
more?
ALMA? In a way, it's done using Lyman alpha forest for hydrogen, deuterium, things like this.
Right. So it becomes more and more practical. So, one of the big technological developments in radio astronomy has been really wide bandwidth heterodyne receivers or back ends that can allow you to look at very, very large bandwidth, and that makes it more and more practical, I think, to do blind searches. So,
Sensitivity, is it okay?
I mean, you need quite a bright radio source, particularly at higher frequencies. Those are rarer. But there's so far there's this one at 0.9, redshift 0.9. There's another one at 0.68, and those are practically the only ones known. But maybe there are many more, and it's a matter of getting the right search strategy. I'm not involved with that, but I know people who've been thinking about that, and it may be more and more practical with new receivers with very wide bandwidth, simultaneous coverage.
David, I have a question. I'm sorry, were you done?
Yeah.
Yeah. To what degree do you see variations in the cosmic ray ionization rate as a function of location in the galaxy?
Yeah, so this is a remarkable thing that I didn't get to. But the variations, particularly the ones determined from H3 plus, are remarkably small. The actual variation in the values that you observe is something like 0.25 in the log to base 10, so 0.25 dex. But all these measurements have observational error, so if you ask what part is attributable to intrinsic variations in the cosmic ray ionization rate, it's only about 0.1 dex, which is 25%. And these are clouds, for H3 plus, they're all within probably a couple of kiloparsecs. But still, it was a very surprising thing how little the dispersion was. And it's very hard for some error in the modeling to explain that. I mean, an error in the modeling could give you a larger observed dispersion, but it can't really reduce the observed dispersion. So that was certainly a surprise of this.
Just another question. I was struck by the fact that you said the chlorine 35 to 37 was the same at this 0.89
Right.
galaxy as here. But you didn't say whether that's 1%, 10%, or,
Oh, well, what is the ratio?
Yes.
Yeah, so...
How different are they, or how close to the same are they given the errors?
Yeah, so I'm not quite sure. So they're the same within the errors. I don't know quite how.
What the errors are.
Yes.
What are the errors?
I don't know. So I don't know what the errors are, but they're actually, I can say in our galaxy, we can probably measure it to maybe 10 or 20%. And it's one of these very large ratios. I always remember from high school chemistry, the atomic weight of chlorine is 13.5. It's not an integer because it's 25% chlorine 37 and 75% chlorine 35. But I don't know, I wasn't involved with this study with ALMA, so I'm not quite sure what the errors are on that.
Do you know any prospects for other isotopic ratios?
Yes, so the sulfur, I think they have sulfur 34 to 32, which again is not huge. I think it's 20. 34 over, sulfur 32 over sulfur 34 is 20.
32 is more.
Yeah, right. So that one's been measured as well, I think.
But you don't know whether that's the same or different.
I can't remember. Sorry, I'm not very well prepared for this. I should have mentioned it without knowing more about it.
I didn't mean to embarrass.
I'm not embarrassed. It's okay. Well, not too embarrassed.
Are there any other?
No more embarrassed than I should be.
Are there any non-embarrassing questions? Like Spicer's news conference. Unfriendly question from this point forward.
Blind from the press conference.
Yeah.
Okay, well, let's...
It's just a belief I have.
not an alternate fact. Okay, well, let's thank David again. And again, David...